So welcome everyone. Welcome to the third lecture of this introduction to quantum optics. Today I'm very pleased to tell you that we have ahead a very interesting class in which we will combine kind of very deep concepts of quantum mechanics, and we will also connect with quantum optics already a lot. And do some technical derivations that include the math of quantum mechanics and will help you get better at it. So I think there will be a good balance between these two things. And in particular, if you remember so far, what we have done is we have reviewed quantum mechanics with pure states, so the standard quantum mechanics that you know, and we have quantized electromagnetic field and quantized the harmonic oscillator. So what we are going to do today is we will start with what will be hopefully something completely new for you, which relates to how to do quantum optics in phase space, if that's even possible. And this is a very interesting topic that connects with many deep concepts about whether quantum noise or quantum uncertainty can be represented somehow in our well-known classical phase space. But before that, I'm going to finally introduce quantum mechanics with mixed states. Probably most of you have heard about mixed states, and maybe even you have studied them in your quantum mechanics courses. But we will spend the first half of this lecture really going slowly through why do we need mixed states, and what is the description of systems in terms of mixed states and quantum mechanics in terms of them. And hopefully this will be very useful for you, not only for quantum optics, but for all your future quantum mechanics research. Okay, so let's then start with quantum mechanics with mixed states. And let me specifically start by why do we need mixed states at all? And I will give you two examples. The first one is about noisy systems, okay? So by noisy systems, I mean the following. So just imagine that you have a system, so you have your experiment, you're an experimentalist, and you want to prepare your quantum mechanical system in some state, and you have a machine for that. So you have a machine that performs quantum state preparation. But of course, in real life, nothing is perfect, so machines come with some noise. So you have always a little bit of noise. Imagine, for example, a magnetic field that is not exactly the value that you think, but it's slightly above or slightly below. And therefore, in real life, you always have what we call imperfect state preparation. So let me write it down. So we have imperfect state preparation. And in particular, what we are going to assume is the situation in which, for example, you know that your machine has prepared a state, but you are not sure exactly for what magnetic field. So then you just know that you have prepared a state, so a pure state psi m, among a set of states. So let's say capital M states. So you have prepared one among these states, but you cannot be sure of which one because, as I said, there is some noise in the system and you cannot be sure exactly of what was the magnetic field. In particular, you know that you have prepared one of these with some probability, omega m. So omega m will be the probability that I prepared the state psi m. So this means that omega m, every time I say that we have a probability distribution, what I mean is that the omega m's are larger or equal to 0, so non-negative, and that they sum up to 1. Okay? Then this is all we know. So we know that the machine prepared some state, but we don't know exactly which one. Now the question is, if I want to describe my experiment, if I want to describe what I observe in my experiment, can I do something, or it is completely hopeless because I am not sure of which state did I prepare? So of course, you know that the answer is that yes, I can do something. And let me explain you exactly what. So basically, quantum mechanics, it's all, when it comes to experiment, it's all about explaining the statistics of the experiment. So when I repeat the experiment many times and I get outcomes and outcomes, what is the statistics of those outcomes? So then now the question is, imagine that I care about one observable, so I care about the statistics of one specific observable. So observable statistics. And imagine, for example, that we are talking about some observable B and we want the expectation value of B. So can I still predict what is the expectation value of B? So what is the average of the outcomes that I will obtain in the experiment, even if I have imperfect state preparation and I don't know what is exactly the state? Well, I can. So in particular, we know that if we would prepare state psi m, this mean value would be generated by what we have called the expectation value of the operator in the state psi. Okay. And then if now we are simply not sure which one appeared, and we have in particular some probability that psi m appeared, all we need to do is average, not only quantum mechanically, but also average over the ensemble, the set of states that we can prepare, okay? So this is very natural, so this will be actually the expectation value or the mean of the outcomes that you will observe in the experiments. But I can rewrite this in a very interesting way, and I can rewrite this in the following way. So I will use, I think for the first time in the course, something that will come with us all the time, which is the trace operation. And the trace operation, so let me define some things about it before giving you the result. So the trace operation is the following. So just in case someone is not familiar with it in the context of quantum mechanics and operators and so on. So when I say that I evaluate the trace of some operator D, okay, what I am saying is that I take the diagonal elements of this operator in some basis of the Hilbert space. So these states here form a basis of the Hilbert space. Okay. And then I just add them up. So it's exactly the same as D is the dimension of the Hilbert space. So it's exactly the same as the trace of a matrix, but this for a general operator in terms of the trace of the representation of the operator in any basis. So what's interesting, and is the first thing that might sound funny, but this is the case, is that even though the trace operation is defined in a way that looks like it depends on the basis that you choose, because you are adding up the diagonal elements of the representation of your operator, actually this is not the case, and it can be shown that this quantity, so the trace of an operator, the trace of a matrix, is independent of the basis. So the trace is basis independent. This is very important because we are going to write everything in terms of traces all the time. And essentially, you now understand that when I write something in terms of a trace, doesn't mean that it's related to a basis, but just a general expression. And then this trace has a couple of important properties. So the first important property is what we call the cyclic property. And the cyclic property simply means the following. So when I evaluate the trace of the product of operators, so imagine I have the product of two operators, this is the same as bringing the operator that is most to the right, bring it completely to the left. So this is equal to bringing this operator here. So D2, D1. And of course, the same works with the operator that is most to the left, bringing it most to the right. Someone tells me that someone raised his hand. Please, if you have questions, really just open your microphone and go ahead, because I cannot see everything.
I'm sorry.
Yes.
I can't see the notes clearly. It is a little vague. I can't see the index or.
Okay, you mean because it's small or?
No. It is maybe it's because of some technical reason. Because in the last lecture, when you quit this app and you open it again, it becomes clearly.
Okay, so let me just stop it and restart. Let me just try again. Okay, so let me go ahead and open it back.
Okay. It's clear now.
Is it clear now?
Yeah.
Okay, so let me just rearrange this so I can see you all. Okay, so we can go ahead. Okay, so thank you. So just if this happens again, just interrupt me again and we check. Okay, so then hopefully now everyone can see it and you are not lost. So let me come back to what I was saying. So what I was saying is that the trace operation can be defined just as the sum of the diagonal elements of the representation of the operator. And even though this is defined in a basis, it's actually basis independent. It doesn't matter which representation you choose for the operator, you will always find the same trace. And this trace has one important property, which we will use all the time, which is the cyclic property, which means that the trace of a product of operators, it's the same if I bring the operator that is most to the right, I bring it to the left, like it's in here, okay? Or the other way around, that the one that is more to the left, I bring it to the right, okay? And then another property that will be useful all the time is that if we evaluate the trace of an operator times an outer product, so a ket-bra structure. So imagine that I evaluate this. This you can show very easily that it's equal to just doing the operation of the operator acting on the ket and then inner product with the bra. Okay, so this is something that we will use a lot of times. So essentially, the trace of an operator times an outer product, okay, it's equal to this kind of more familiar object. Okay, so now that you know what is the trace, let me just tell you, or I hope you can see it very easily, that now I can rewrite this. Specifically, I can rewrite this using this property here. I can rewrite it in this very nice way, in which I use the trace, and now I do the sum over all states. So the projectors of all states. So this is all one object acting on B. Okay? So this is very interesting because now you see that all the information about imperfect state preparation, so all the information about what is the state that I have with what probability and so on, it's contained in a single object, and we will call this object by the name rho, and this is what we will define, or what we define as mixed state. Okay, so you have seen in here that mixed states, or this kind of object, okay, this kind of object appears naturally when we have some noise in the system and we are not sure about which state did we prepare, and in particular, we say that this setting here, so the states that I can prepare with what probability, we call it an ensemble decomposition. So ensemble decomposition of our mixed state rho, okay? It's very important that you understand a couple of things. First of all, these states psi m, of course they are normalized, so their norm is 1, but they do not need to be orthogonal to each other. I mean, this is very easy to understand because actually when the problem comes because there is some noise in the system, of course, the value of the magnetic field that we want and the value with noise, they are very close. So they don't generate orthogonal states in general. They generate states that are very close. So then in general, the states of the ensemble are not orthogonal states. These states are not orthogonal. And the number of states that we have in the ensemble has nothing to do with the dimension of the Hilbert space, okay? We could have a Hilbert space dimension 2 and have m equal 100, or we could have a Hilbert space dimension 100 and have m equal 2, okay? So I hope that this is clear. Then let me give you one specific example of this imperfect state preparation that it's actually very interesting in general as a definition. And this is something that is known as non-selective measurements. Okay, non-selective measurements. So you will understand in a second what this means. It's very simple. So imagine that I want to measure an observable. So I measure an observable A in the lab, okay, that I can represent in its eigenbasis in this way that we have already used many times, okay? But now I have the following problem. I have the problem that I have performed a measurement, but the machine I am using to perform the measurement is broken. And in particular, the screen, I cannot see it. The screen is broken, and I don't see what is the outcome of the experiment, okay? I know I performed a measurement, but I don't know what was the outcome. Now the question is, so let me say that I measure A, but the meter is broken. Okay. Now the question is, can I still predict things about the statistics of the experiment, either just the statistics of the measurements after I do many measurements, or even I want to do things after the measurement. I have my lab, I have a protocol, and the measurement was just the beginning of a protocol, and I want to predict everything that comes after. So now the question is, can I do this with some state? Well, we have learned about mixed states. And the question is, we know that a measurement took place. But we don't know the outcome. So this is the only thing. Oops. Okay, so this is precisely the situation that I have just described. So in particular, we can create a mixed state that will contain all these statistics because we know that after the measurement, because of the collapse postulate, we know that one of the states A has been prepared. But we just don't know what, so which one. We know that it has been one of these with probability Pj, where the probability Pj is just the quantum mechanical probability that we know. So if the state was psi prior to the measurement, so the state was psi, this is the probability of obtaining outcome AI, or AJ, sorry. And essentially all I have to do is do the sum from 1 to D, because now A is a basis of the Hilbert space, because A was an operator that is unobservable. But essentially now, all the statistics of my experiment will be recovered just with this kind of mixed state, okay? So we call this non-selective measurement because we perform a measurement, but the measurement doesn't select or doesn't allow us to select one of the eigenstates of the operator. We just know that we created one eigenstate, but we just don't know which one. We just know the probability that one appeared. Okay, so I hope that this was an interesting example in the sense that it shows very naturally how mixed states appear in quantum mechanics, in real physical systems. And now let me give you another example. So now it's a different kind of example. So now it's about composite systems and how when we have a system that has two parts, A and B, like we described last week, and we want to analyze what happens in one of the subsystems, one of the parts, then mixed states appear also very naturally, even if the whole state is pure, okay? So let's do this slowly. So as I said, let's consider here a composite system. Okay, we consider a composite system with Hilbert space that, using the same notation as last week, is the tensor product of two Hilbert spaces A and B. And we assume that the whole system is in some state. So some state that could be pure or in general is just a mixed state of the whole system, okay? So we will later particularize to when the state of the whole system, so this is a state of the whole Hilbert space, it's pure, okay? But for now, let me just take it mixed that we have learned from the previous section that they can appear. So let's just take it. So now I ask you the following question. So imagine that I take subsystem A and I give subsystem A to an experimentalist that I can call Alice, okay? I give that subsystem to Alice, and I don't even tell her that it's a part of a bigger system, that it might share correlations and entanglement with another subsystem. I just give her that system, and I tell her, okay, do experiments, do whatever you want with subsystem A, okay? Now the question is, can Alice, so can this experimentalist describe her experiments using only elements, so states, operators, and so on, in her Hilbert space, and the Hilbert space of her subsystem? So, of course, the question is going to be yes, but the question is this possible, or would she need every time that I tell her, no, this is part of another system and this is the whole Hilbert space of the whole system? Okay, so the question is set, and the answer, let me just explain you, so give you the answer right away and then explain you in detail. So yes, she can, with something called the reduced state. So the reduced state, in this case of system A. So we have here the whole state rho, okay, the whole mixed state. But now what I am going to show you, I will prove it in a second, is that Alice can recover the statistics of her experiments in this way. She can, or we can define something that we will call reduced state of A, which means performing an operation onto the whole state rho that we will call the partial trace. So this is the trace, but only over subspace B. And the definition of this, the formal definition of this, is this thing in here. So imagine that I take a basis of the space B. So these elements here are a basis of the Hilbert space B. So this means that I take the operator that is acting on the full Hilbert space, so in A tensor B, and now I just do this sandwich, I do these products only with the basis of space B. So of course, what I am going to obtain when I do this process, it's going to be an operator that acts only on A. And this, let me show you in detail, so you have some more familiarity with this kind of operations. So in particular, the way to see that this is an operator acting on A is the following. So we can represent the full state rho. We can represent it in a basis of the full Hilbert space, right? But we already know a basis of the full Hilbert space based on the basis of subsystems A and B. We already talked about this last week. And in particular, now you know that you can represent this state in the basis that last week we call EM, EB. So this ket means the tensor product between the basis element M of A and the basis element N of B, if you remember. And then, so we will have the matrix elements, and we just have some elements in this basis that we can call rho M, M prime, and N prime, and then the sums over M and M prime go from 1 to the dimension of A, and then from 1 to the dimension of B. Okay? So this is just a general representation of my state in the full system, just in the basis of the full system with, okay, some elements that have now more indices because you have to keep track of which index in which subsystem. But the only important thing is that you remember that this notation here is completely equivalent to this notation here with the tensor product. So I just take the outer product between the A states and then the tensor product with the outer product of the B states. Okay, I hope that everyone is familiar with this. So this is something that we, I don't know if we wrote it explicitly, but from last week's discussion, I hope it's clear. So then now this means that automatically, look what happens. I have my full state rho, and then I have to operate with this bra and with this ket, okay? So when I take this full state and I operate with this bra EB and with this ket EB, what happens is that I am acting only on the part of the tensor product that corresponds to B, okay? And in particular, when I take EBL and I do the scalar product with EBN, what I obtain is a Kronecker delta of Ln. And the same happens here. I will get a Kronecker delta of Ln prime. So then finally, what I get is something that looks like this. So I can remove the sums over B. I only have to sum over A because the Kronecker deltas have destroyed the sum over B. And then I get just the basis elements evaluated in N equal L, N prime equal L, okay? But I still have the projectors or the matrix elements, so the outer products, onto the A subspace. So this clearly is an operator that acts on subspace A, okay? So I know that this took a little bit of time, but I just want you to get familiar and get really, really like comfortable with what's a trace over one subsystem, what we call the partial trace. So the partial trace over subsystem B gives you an operator that acts on subsystem A, and just applying this operation that we defined in here onto this state. So, okay, very good. Now you know what is the partial trace, but I still haven't proven to you that this state, the reduced state that we have defined, it's actually the state that Alice, the experimentalist who only has subsystem A and doesn't know anything about another subsystem B, has in her lab. So let me just prove this to you now very easily. So the proof of this is very simple. So as I said, quantum mechanics is about reproducing statistics. So for Alice, what's important is the following question is, what do I need to reproduce the statistics of my observables? Okay, so if I have an operator, an observable A that I want to perform statistics on and so on, what is the expectation value of this operator? So for her, this just means calculating the expectation value of her operator. But for us that we know that everything is part of a larger space, this means that she's taking the expectation value of some operator in her subspace that acts as the identity, so acts trivially on subspace B, okay? Therefore, essentially we need to calculate this. And we have learned from the previous section that if I want to calculate the expectation value of this operator in a mixed state rho, so remember that the general state of the system is some state rho, I can do it just with the trace of rho acting on the operator I am interested in. So this is simply comes from the previous slide in which we already said that the expectation value of any operator B is just the trace of the mixed state times the operator, okay? So then, now I can start rewriting this expression in terms of my basis elements. And in particular, I have to remember the trace means I have to sum the diagonal elements of my representation. So the diagonal elements of the representation of this operator in the full space. So this means that I will have two sums, and I have to sum the diagonal elements in my basis. So my basis in the full Hilbert space is this, where here I have to sum from 1 to A so the dimension of A from J, and from 1 to dB for L. And then to this, so I have to apply this on the operator A times the identity. And now here I will have just the basis elements. Oops, sorry. So is it clear for everyone that this is the trace? So remember, this is the basis of the Hilbert space, but we have to sum over all the possibilities of the indices J and L, and the trace is defined just as the diagonal elements of this operator in this basis, which means that the indices of the brass have to be the same as the indices of the kets, okay? So I hope that this is clear. Now, this is very interesting because I have written the tensor products explicitly. So you see that now we have this operator has a tensor product structure, and these vectors here have a tensor product structure. So then when I say that this operator acts on this vector, what I mean is that A acts on this vector of A, and the identity, so nothing, acts on this vector in B. So overall, this state here is just the state in which I have applied A to the vector in A, but I have done nothing to the vector in L, sorry, in B. Okay? But now, this is very nice because you see that so this operator A does not depend on the index L at all, right? So this means that now I can take all the part of the sum in L, including this, the sum, and this. I can bring it all the way to act over the state rho. And therefore, what I get is the sum over J. This is still outside. Now I have my vectors in A. But now I have the sum over L of my vectors in B acting on rho. And then all of this is acting onto the operator A acting on EJ. Okay? So I hope this is clear. So I have just combined together all the things that have dependence on subsystem B or dependence on indices L. But what is this object here? This object here is exactly the reduced state that we have defined in here. So in other words, this is just the trace over subsystem A of the reduced state A. Let me maybe make some space. So you don't see things too crowded. So it's the trace over subsystem A of the reduced state A times the operator A, okay? So this is very cool because this is telling you that from the point of view of Alice, so for Alice, performing an expectation value means just doing the trace over her subsystem A. So from the point of view of Alice, everything, so all the statistics of A or the statistics of her experiment can be reproduced just from a state, rho, that belongs only to subspace A. Okay. So then this is the proof that you can describe the physics of a local part of a bigger system. You can describe it with what we call the reduced state by tracing out all the rest of degrees of freedom. And this is something that we will use in quantum optics in the second half of the course a lot. So is this clear? So otherwise, please remember, just unmute yourself and ask away. So this is a completely general result for any state of the full system, rho. But let me now particularize this result. Sorry. Sorry, so many technical problems today. Okay, I'm back. Okay, so let me just particularize this to the case in which the state of the full system is pure. So what I want to show you is that even if the state of the full system is a pure state psi, the reduced state from the point of view of Alice, who only has a subsystem, it's a mixed state. And for this, we will prove it in a very simple way. So in particular, I hope that it's completely clear to you that any pure state psi, I can always represent it in the following way. So this is completely general. So let me write it down and then we discussed it. Okay, so what am I doing here? So I have a state, and I can always choose a basis of the Hilbert space B, and I can combine all the things that appear multiplying, either with tensor product or with a scalar product, it doesn't matter. Sorry, with standard product. So I can combine all the things that appear in front of these basis elements into one object, and that will be a valid representation of my state. So all I'm saying is that you can always represent your state as the tensor product of the basis, some basis elements, whatever basis you want, doesn't matter which one, any basis of system B times some states normalized of your subsystem A, and then some probability amplitudes here. So these omega m are a probability distribution, okay? Just by normalization of the state. So I hope this is obvious for you, but otherwise think about it later, and if it's not clear, we can discuss more. But if you give me that, so if you allow me that this is any valid representation, then if I want to evaluate the state in subsystem A, as we have discussed, I just have to perform the trace over B of this pure state psi. But this is equal to what? So I just have to look in here. I have to rewrite the state psi in this way, which means that I will have a double sum in m prime of the amplitudes of m and m prime, then the states psi m and psi m prime, and then I will have the product or the tensor product of that with the basis vectors of B, m, and m prime. And now I have the trace operation, but the trace operation, so this operation here is an operation only on subsystem B, so I can bring it all the way to the operators on subsystem B. But we have already discussed this property of the trace, that the trace of an outer product is equal to just the inner product of the corresponding vectors. Okay, then when I use this Kronecker delta onto the full sum, what do I get? Surprise, surprise, I get this state here. So this mixed state here. So you should be familiar with this because this is exactly the same kind of state, what we call a mixed state that we obtain for noisy systems. So for noisy systems, we also obtain very naturally the mixed state formulation. So as you see, this formulation of mixed states, okay, appears all the time in any situation in quantum mechanics that goes beyond, let's say, the standard situation of having a single system that we prepared perfectly from the beginning. So, but this example allows us to discuss something very, very interesting that will also help you for many things in the future in quantum mechanics, which is the following. So let me write it down and then we discuss it. And the statement is that ensemble decompositions are not unique. Okay, so what does this mean? This means that I have built some mixed state rho as a mixture. We will call this kind of object mixture of projectors, okay, of some states psi with some probability distribution. But we can show now that actually there are many other, infinitely many, yeah, basically infinitely many ensemble decompositions for the same operator rho, for the same state. And the way to see it, it's very trivial in this case of subsystems, because instead of representing my state psi in a basis E of subsystem B, I can choose another basis, right? So as I said, this basis is completely arbitrary. So I can do a change of basis. So let's do a change of basis in system B. And in particular, now we will take other basis elements that we will call D. And of course, you know from basic algebra that two bases of the Hilbert space have to be related by a unitary transformation. So let me write it down. So essentially, we are changing from the basis E to another basis D with the same number of elements, dB, which are connected by some unitary transformation. So then if we do this change, then we can rewrite our state psi, okay? We simply do the basis change in there, and then we can rewrite it in this way. So psi will be equal to a sum over now over k, okay? Because we are in the basis elements D. But now we can combine everything else into some other states and some other probability distribution. In particular, with the definition that we have defined the probability distribution amplitude times psi k, phi k, sorry, as the sum over m of the unitary acting on the amplitude and states in the other representation. So is this clear? So the only thing I did is just taken this expression here, I substitute it in here, okay? And then I combine everything that depends on m, I combine it together in something that I call square root of vk phi k. So of course, the probabilities vk, they come very naturally. So this you can find from the normalization of the states phi k. So the phi k's are states in the Hilbert space, therefore they have to be normalized. So they are not orthogonal, again, okay? They don't need to be orthogonal, but they can be normalized, and from this expression you find the probabilities vk. But then, if now you would apply the same kind of derivation that we did in here, so all this derivation, but instead of doing the trace with a basis, with the basis E, you would do the trace with the basis D, which is also allowed. You would obtain that rho A, which is the same operator, the operator doesn't change. It's written in this way, summing k from 1 to dB of vk phi k phi k, okay? And of course, these two operators, as I said, they are the same. That doesn't depend on the operator, sorry, on the basis. But as you see, the ensemble decomposition is different because these states psi and these states phi are not the same, and these probability distributions W and V are not the same. okay? So then you can see how ensemble decompositions associated to a mixed state are not unique. So therefore, you have to be very careful. When I give you an ensemble decomposition, that doesn't mean that in reality, like in the physical space, okay, I could be in one of the, or I must be in one of the states of the decomposition, but I don't know which one exactly, okay? That's just a representation of the mixture, but there are many representations of the mixture, and all of them need to be interpreted with a lot of care, okay? Maybe we will see some more examples about this, but be careful with associating these states phi, psi, or these states phi with any real state that has appeared in your experiment, okay? So I hope this is also clear. And then now, let me move on to finally start getting some intuition about what is this mixedness, these mixed states, what are they all about, and how can we understand where the mixture is coming from an intuitive point of view. So maybe I come back for a second, and in all these two examples that we discussed, the mixedness appeared because of some kind of ignorance that we had. For example, in the case of noisy systems, is the ignorance that, okay, the meter is broken, and therefore we know that one state appeared, but we don't know which one. So we have some ignorance there. Then on the other hand, in the case of a subsystem, our ignorance, or if you want, Alice's ignorance, comes from the fact that she doesn't know that part of the information of her system is correlated with another system. And therefore, she has not access, okay, she doesn't have access to part of the information of her system that has leaked out to another subsystem. Therefore, I think it's very important that you keep in mind, and this will help you a lot every time you work with mixed states, that the mixture of a mixed state, so mixture simply represents, it reflects our ignorance. Whether classical ignorance about classical noise or quantum ignorance about entanglement with another system and quantum correlations that we don't know, okay, we don't have access to. So, and to give you a bit more arguments of how this is the case, I could ask you something like, so if mixture is just ignorance, can I write down the mixed state that has leaked out the maximum amount of information, let's say all information about the system? So the state that satisfies this requirement, so all the information about our system has gone out of the system, either in terms of quantum correlations or classical correlations with another system, and we will call this state the maximally mixed state. Okay, so this is just as mixed as you can be. So let me argue that actually we have a very simple state, mixed state, which is the maximally mixed state in dimension D. And this is just the identity normalized to D, okay? So let me just let you know that the case of dimension going to infinity, we will treat it next week. Okay, because when the dimension goes to infinity, then this doesn't make too much sense because you would have kind of an infinity in the denominator and then an identity that has trace infinity in the numerator. So it's a bit of a difficult object. But in finite dimension, so for finite D, let me now argue that this state, so a mixed state that is proportional to the identity, is the state that has leaked out the maximum amount of information. So maybe it's a good point also to tell you that this divided by d comes from the fact that, of course, the trace of the mixed state is equal to 1. So we can see it from any expression that you want. So for example, the mixed state rho A, which is equal to the sum of projectors, if you just do the trace of this expression, you get the norm of this, which is 1, because this vector is normalized, and then the sum over the distribution, Wm, and if this is a distribution, this has to be 1, okay? So all mixed states that I have presented so far, all of them have trace 1. So this is kind of telling you that you need to normalize the states, the mixed state, to having trace 1. And this is equivalent to normalizing the pure states to 1. Okay, so now let me argue that this is the state that has leaked out the maximum amount of information possible. And let me do this in the following way. So imagine that I picked an arbitrary operator. So I have A, so an arbitrary observable, and I perform a measurement. So again, A is any operator of your system, you perform a measurement, then you know that the eigenvalue Aj will appear with probability Pj, right? But now the probability Pj, how do I calculate it? How do I evaluate it? So one way of calculating probabilities is just as the expectation value of the corresponding projector, okay? So this is an expression I am giving you because it's actually very useful in general. But of course, for pure states, this is completely trivial because the corresponding expectation value, you just need to put in here psi, psi, and then you get a psi square. But in general, for any mixed state, like the one we are dealing with, this means that we have to evaluate the trace of rho times the operator, okay? But as we have seen, this is just equal to Aj rho Aj, and since rho is just equal to the identity, this quantity here is just equal to 1 over d, okay? And what's very important is that it's 1 over d for all j, so all eigenvalues have the same probability 1 over d of appearing, and even more important, for all observables, for absolutely all observables. So if I take any observable in my system and I perform a measurement, I cannot predict anything about what will be the outcome. All outcomes are equally likely with the same probability. So we have a flat distribution. So a flat distribution of outcomes for all observables. Okay. So this is amazing. So I am telling you that I have given you a system, but I have prepared it in a state that has absolutely no information, in the sense that you cannot predict anything about when you do a measurement, what will be the outcome that comes. Okay, this is the absolutely most random state that you can imagine in quantum mechanics. Okay, so is this clear? Because if this is clear, I will move on to just tell you something about, we have discussed what is mixedness and how mixedness appear, but how about quantifying it? Can we quantify it? Okay, so the question is, we have seen that there are states that are pure and therefore have no mixedness. we have seen now that there are some states that have no information at all, and that's what intuitively we would call the most mixed or the maximally mixed states. But how about in between? So how mixed is a state that I give you? So I give you a state rho, and I ask you, how mixed is it? Well, there is a quantity that we will call S of the state rho, that it's, the name that it received is von Neumann entropy, okay? That precisely gives you this. So it quantifies how much mixedness or how mixed is your state. So in particular, this can be calculated, or this can be defined in the following way. Again, a trace of the expectation value of a very special operator is the logarithm of the state itself, okay? So minus trace rho log rho. Okay, this looks very weird, like, okay, it looks very random, like why this object and not any other? So let me argue in very simple terms. So what happens when you take your mixed state rho and you diagonalize it? So you find the eigenvectors and eigenvalues. So rho, we have seen that rho is a Hermitian operator, and therefore the eigenvalues are positive, are real. On the other hand, it can be shown very easily that because of this probability interpretation and so on, the eigenvalues also need to be positive and actually bounded by 1. But this is not very important at the moment. What's important at the moment is that we can diagonalize it, which means that we can write an expression like this for the density operator, for the mixed state rho. We can write it like this, where these vectors are a basis of the Hilbert space with dimension d. And therefore, in this basis, the calculation is trivial. Using the spectral theorem, this is just j equal 1 to d, rj log rj. Now, like I said, this, if you remember, the trace of rho has to be 1, which means that these objects in here, because the trace is just the sum of all r's, okay, these have to add up to 1, which means that they are a probability distribution. And therefore, this quantity here, now we know that this is something called the Shannon entropy, which is a quantity defined for classical probability distributions in the context of classical information theory. So I know that you probably haven't studied information theory, but I just want to give you the feeling that at the end of the day, this von Neumann entropy is nothing but the, let's say, the classical informational entropy, the classical Shannon entropy of the probability distribution associated to the mixed state. And therefore, everything, all the concepts that we have about classical information theory, and this has been developed a lot. I mean, all our world is based nowadays on information theory, classical information theory. So all the concepts that we have about what is this Shannon entropy, they can be applied to this quantity, von Neumann entropy. And in particular, it's very easy to actually see that this Shannon entropy quantifies somehow what is the information contained in the probability distribution R, okay? So, but of course, on a more simple level, you can just check very easily two limits. First, the limit in which rho is a pure state. So if rho can be written as a projector, then you can check that this von Neumann entropy is equal to 0 very easily. And if rho is the maximally mixed state, then what you can check is that this is equal to logarithm of d, which for a given dimension D is actually the maximum of this expression, okay? So you have a maximum entropy of log D for a Hilbert space dimension D that you achieve when you are in the maximally mixed state, that is the identity. And you have 0 entropy for a mixed state rho, okay? So at least this is telling you that this quantity is quantifying well the two limits, the two extremes, in which by informational arguments, we know what is the concept of mixedness, okay? So if this is clear, then before the break, let me just conclude kind of reformulating quantum mechanics with mixed states. So we have formulated quantum mechanics with pure states. Now that you know that in general, you need mixed states to describe real physical systems that might be correlated with something else, whether it's a device, a measurement device, or it's another quantum system. And therefore, now we can redefine quantum mechanics in terms of these mixed states. So actually most of the postulates of quantum mechanics remain exactly the same, or are the same kind of postulate. Now with only a few differences. In particular, the state of the system. So the state of the system now is not associated with a vector in the Hilbert space. It's associated with what we call a density operator, rho, which is the mixed state that we have discussed before. And when I say density operator, so a density operator in mathematics, it's something that has very concrete properties. In particular, it is Hermitian, so it is self-adjoint. It is positive, so, or better, non-negative. This simply means that the eigenvalues or the expectation value of the operator in any state cannot be negative. They can be only 0 or positive, and it has a finite trace, which means that you can always normalize it. You can always choose the trace of this operator to be 1, okay? Then any operator that satisfies this, self-adjoint, positive eigenvalues or non-negative eigenvalues, and trace equal 1, that's a valid quantum mechanical state. And these properties are actually very interesting because they tell you that the diagonal elements of the representation of this density operator in any basis of the Hilbert space, so J goes from 1 to the dimension D, these diagonal elements, because of these properties, first of all, because it is Hermitian, these have to be real. Second, because they are, it is a positive semi-definite object, then this cannot be negative. So they have to be positive. And because the trace, we have normalized it to 1, these elements are bounded by 1. So they are always between 0 and 1. So therefore, density operators, we can say that they encode probability distributions in any basis. So the diagonal of the representation of your density operator in any basis, it doesn't matter which basis, that diagonal, it's always a probability distribution. And then we can update now the measurement postulate in the following way. So when we perform a measurement of an observable, which still is defined by, or is represented in quantum mechanics by a self-adjoint operator that has a spectrum given by this formula here, then when we measure, eigenvalue Aj appears with a probability that is given precisely by the diagonal elements of the density operator in the eigenbasis of the operator that we are observing. And this, as I have discussed before, this can be written in a basis-independent way as the trace of the projector AJ. Okay? So this is how we can evaluate now probabilities given a mixed state, a density operator. And then finally, the other postulate that we have to update refers to unsupervised evolution. So remember that unsupervised evolution means that we don't do anything on the system and the system evolves in time according to a unitary operator that is the exponential of I times the Hamiltonian. And then if our state is mixed instead of pure, we have to change the Schrödinger equation, and instead of the Schrödinger equation, we will write something equivalent for mixed states, that is the following. So the state of the system, represented now by a density operator, by a mixed state, at time t, is just the state of the system at time 0 in the Schrödinger picture, and then we just do a transformation with the unitary evolution operator, a transformation of this type. Why is this the case? It's actually very simple. So this is obvious. When I represent my state rho, when I represent it in an ensemble decomposition. So if I do an ensemble decomposition of my state, any ensemble decomposition, because we have many, so any of them, you will be able to write it in this way. So this is a mixture of pure states, and each of the pure states evolves with the unitary evolution operator exactly in this way. So psi mt is equal to the unitary operator u, so the time evolution operator, acting on psi of 0. And here we have the bra instead of the ket, so we will have u dagger. So in total, the mixed state at time 0, so the mixture at time 0, is nothing but, so it's equal to the mixture at time t connected with the unitary operator, unitary time evolution operator, okay? And then to finalize, of course, this has a differential form instead of this unitary form, just like the Schrödinger equation and the Heisenberg equation that we showed before, that is this one. So if I take the derivative in time of this expression, I can rewrite it in this way. Okay, and this equation is known as the Phon Neumann equation. And there is something very interesting about this equation. First of all, do not confuse it with the Heisenberg equation of observables. This is still happening in the Schrödinger picture. So rho represents the state of the system, okay? And the state is evolving in time. So we are in the Schrödinger picture. We are not in the Heisenberg picture. And this equation here is not the same as the Heisenberg equation for the observables, because if you remember, the equation for the observables was not that the time derivative of the observable was the commutator of h with the observable, but the observable with h. So there is a minus sign in this expression with respect to the Heisenberg equation of motion. So do not confuse it with the Heisenberg equation, please. Okay, so it's kind of perfect. I hope I didn't go too fast. Again, this has, so all the details about this and all the speech and everything, you have it exactly, even much better than I explained it in the lecture notes. So go there and read them carefully. And I will also give you an exercise related to mixed states. So you get comfortable calculating with them and so on. So let's take a little break and see you all in 10 minutes. So welcome back. Let's now change completely the topic, but this is a topic that requires already mixed states. This is why I introduced it. So now we are going to talk about whether we can kind of discuss quantum physics in phase space, in the classical phase space made by position and momentum variables. And the question has a positive answer in a certain way. We still can visualize quantum mechanics with the use of something that we will define that is called the Wigner function. But it's a little bit more subtle than just noise acting on the space. And this is very important for you to know in general as well, not only for quantum optics. So then let's go with it. Okay, so let me just introduce it by kind of pointing something at you that is the following. So first of all, position and momentum. So the position and momentum quadratures that are that we have defined in our case, just some normalized position and momentum. Essentially, the eigenstates we saw that they form a continuum, and therefore they are not physical. Okay, so position and momentum eigenstates are not physical. But on top of that, X and P do not commute, and therefore they do not possess common eigenstates. Okay, then these two properties combined tell us that in quantum mechanics, it is impossible to prepare states, so to prepare the system in some state where or in which the quadratures, so in particular position and momentum, take definite values. Okay. First of all, because if we make one very well defined, then the distribution of values in the other will just become very wide. And second, because since the eigenstates are not physical, if we try to create one eigenstate, we will not be able. So we always have some kind of distribution, maybe very, very, very peaked. So very, very much in one mean, but always with some kind of uncertainty, some kind of width. Then in quantum mechanics, we have to abandon this concept that we can give well-defined values of position and momentum, and instead, the most we can offer in quantum mechanics are the probability density functions associated with position. So this will be the position probability density function. So let me just remind you here that PDF is not the type of file, but it's the simplified notation for probability density function. Okay. And so as I said, the best that we can give is the probability density function associated with position measurements, or the probability density function associated to momentum measurements. So that we will just write in this way. Okay. So I remind you that this form of the probability density function for pure states would be something like x psi square, but for mixed states, we already saw that you can always write it in this interesting way in terms of the density operator. So, but now the question is the following. Okay, so I cannot have well-defined values for positional momentum, but can I still define this, this uncertainty, this blurriness in positional momentum, so this blurriness in phase space, can I still describe it with some kind of probability distribution around some kind of average? So in particular, the question would be, okay, is it possible for me to describe these probability density functions So is it possible to describe them through a combined probability density function that we will just call W for Wigner? We will put a subindex rho representing which quantum mechanical state we are referring to. And then we have some coordinates R that are just the coordinates in phase space. So these are just the positional momentum coordinates in phase space. So the question is, we have probability distribution for X, we have probability distribution for P. Can we describe these distributions, so the whole uncertainty in quantum physics by some probability distribution in phase space? Okay. So the answer is actually partially yes. So we will, I will show you what I mean by partially. And in particular, we are going to do it through something called the Wigner function, okay, that we will represent by this W. And the Wigner function is built in a very simple way, because the most natural way of asking what is this probability density function in the total phase space, so two variable function, two variable distribution, is just by demanding that if I calculate the marginals of the distribution, so if I take the distribution and I calculate the integration over momenta, so I just integrate out momenta, then I get the probability density function of positions. And if I integrate out the positions, then I get the momentum probability density function. So if I require these two things, okay, that the PDF of position and the PDF of momentum appears as marginals of my total distribution in phase space, this automatically fixes some definition of this object, and in particular, the Wigner function. So let me then introduce what is this Wigner function, and I will show you how this is the case. And before introducing the Wigner function, I just give you a couple of definitions. So the first definition is that just like we define the coordinate vector in phase space, in the classical phase space of positional momentum, we are going to describe also, or we are going to define also a vector that contains the corresponding quantum mechanical operators. Okay, so this is just a two-dimensional vector which has operators as components. Now, in terms of this vector R, the commutation relations between positional momentum can be written in a very compact way, which is the following. So if I evaluate the commutator between component M and component N of this vector, I can define a matrix M, so omega Mn, and this matrix has a very special form. In particular, it has this form. So it has zeros in the diagonal and 1 and minus 1 in the anti-diagonal. And this is known in mathematics and in algebra as the symplectic form. So perhaps you are familiar with the concept of form from mathematics. We call form in mathematics to objects that are, or matrices, objects in general, that are completely antisymmetric. This means that if you exchange any two indices, you get the minus of the previous permutation. So in this case, this is a form in that sense because it's completely antisymmetric. If you exchange any two indices, you get minus what you had before. And this is why you get zeros in the diagonal, and this is why you get 1 and minus 1 in the anti-diagonal. So there is one property that it's interesting, or two properties that are interesting. First of all, the transpose, it's equal to minus the matrix itself. And actually, the inverse of the matrix is equal to the transpose, okay? So these are just two interesting properties. So for now, don't take it like anything very special. We just give it a name called symplectic form. But actually, the fact that we have this symplectic form gives us an amazing algebraic structure that appears in phase space, both in classical and quantum mechanics, and can be exploited, as we will see a little bit here. Okay, the second thing I want to define is something that we will call D of R. So it's an operator that depends on the phase space variables, and we call it displacement operator. And we can define it in the following way. So we define it just as the exponential of I/2 R transpose omega R. This is a very fancy way of saying I/2 P x minus x P. Okay, so this is just the exponential of something that is linear in position and momentum, and in particular, it's just the momentum times the position. So the momentum in phase space times the position operator, and the position in phase space times the momentum operator. And if you just look at it by parts, so forget for a second about, or forget for example about this. Imagine that you set P equal to 0. This thing here becomes just the translation operator. So it's the operator that makes a translation in real space, okay? As we saw in the last lecture, and you have seen in your courses in quantum mechanics. And similarly, if you set X equal to 0, then what you get is translations of momentum, okay? So then somehow this displacement operator, it's nothing but a combination of translations in position and translations in momentum, okay? And the reason why we put this minus sign in here, well, there are a couple of reasons, but it's because all the structure, all the algebraic structure associated to phase space will appear most naturally because of the commutation relations and so on. And in particular, now I want to make you feel a little bit more comfortable with this notation, because these kind of objects, so this multiplication, so let me maybe write it down. So we will have all the time objects like this one appearing, in which we take one vector y and one vector x, and we calculate the scalar product between x and y but mediated with one of these symplectic forms. And what this does is always the same. The symplectic form, you can see that it's essentially what it does. It simply exchanges the first and second components and puts a minus relative sign between the first and the second component, which means that essentially every time that you have an expression like this, you have to think that you take the first component of my vector to the left and the second component of the vector to the left, and I multiply it with the second component of the vector in the right and the first component of the vector in the right, and I put a minus sign relative, okay? So this will appear all the time, so then it's important that you keep it in mind. So this is just a remark. And then another two interesting things that you need to keep in mind are definitions of the delta function, the Dirac delta function. So you know the definition of the Dirac delta function, that is this one. So this is kind of one of the definitions that you know very well. So let me write it down properly. Okay, so if I tell you that I do the integration of the exponential of IXP over X, then this gives me 2 pi times the delta function in P, okay? But in our case, you see that we always have this kind of 1/2 factors and probably signs and so on. So it's important to also remark that you can do a variable change and change X by X over 2. And then you would get here a 4 and you would get here a I over 2. So this is also true. So the integration in dx over 4 pi of the exponential of I over 2 xp, that's also the delta function. Then similarly, we can do things in 2 dimensions that we will also need. So typically you would say something like this 2 pi square over the real 2-dimensional space of the exponential of I R S, so R transpose S. This is equal to the 2-dimensional delta function in S. Okay, now what we will have is just something very simple. If I put here an omega, everything stays the same. If I replace the I by I over 2, this stays the same as long as I do the corresponding variable change of R by R over 2 in the integration. So I get a 4 pi, okay? So these things here are kind of, so these things in here are things that will be appearing all the time, okay, in the derivations that we are going to do. So I just want you to get familiar with that. This introduction of the omega and the 1/2 doesn't change anything about what you know. It just changes a little bit the numbers that appear. So just keep these things in mind, okay? And let me put them out for the time being. Okay, and let me continue with the definition of the Wigner function. So now that you are familiar with this, so then we have defined the vector of quadratures. We have defined the displacement operator, and now we can define something that is the expectation value in any state that we are in. So the expectation value of the displacement operator. And this is an object that we are going to give it a name, chi, and we call it the quantum characteristic function. Okay. And as I said, it's just the expectation value of the displacement operator, which in terms of the state, so any state, mixed state rho that we have, is just the trace of the state and then the displacement operator. Okay. So then we go to the final definition. So with these intermediate definitions, then I can finally define for you the Wigner function. So the Wigner function defined in phase space, it's just the Fourier transform and so it's just the Fourier transform. So I have to put here the Fourier kernel, but I do it with this omega n 1/2 that we have discussed of the characteristic function. This is why we call chi the characteristic function, because if we perform the Fourier transform, we obtain the distribution or the function that has the properties that I told you before that we wanted. This is what we call Wigner function. So this is what we call Wigner function. And I will show you now that this distribution is exactly the distribution that satisfies this. So it satisfies that the marginals of the distribution coincide with the PDFs for position and momentum measurements. And I will give you a few more properties that will show you how we can do quantum mechanics with this distribution in phase space and up to which point we can do this kind of thing. So let me start just by initially by proving certain properties. So properties of this distribution or this function. I will call it distribution sometimes, but you will see that it's a bit more difficult than just a classical distribution. So first of all, I want to show you that it has the right marginals, okay? So this is the only proof I am going to do in detail because I think it's good if you see how to make these derivations. The rest of the properties, I will just give them to you, and you have all the proofs in all sorts of detail. You have them in the lecture notes. So please go there and do the proofs by yourself. And every step that you don't understand, come to me and ask. But let me prove to you that if we calculate the momentum integral of the distribution that I just defined, we will get the PDF for position measurements. And the idea is very simple. So we just take the form that I just gave you in terms of this, okay, the Fourier transform of the expectation value of the displacement operator. And I introduce the momentum integral. So let me put here the Fourier transform let me put only one 4 pi, and the other 4 pi, I will keep it in the momentum integral. And now I do the following. So we have this Fourier kernel, so this exponential, and I will just split this multiplication, okay? So I will split r prime, so I'm calling r prime the integration, sorry, r prime. And then I split the exponential into one part that depends on the position. Okay, sorry, let me make more space. So one part that depends on the position and the other part that depends on the momentum. And then we have the characteristic function that depends on r prime. Okay, so then now you see that this in here, as I just showed you, this is just the delta function of x prime. Okay, so this means that the integration in here over x prime, we can remove it and we can set in r prime, we can set x prime to 0, which means that essentially this is equal to the integration over dp prime only the exponential that we have already of x prime p, sorry, x p prime. And now we have to evaluate the characteristic function, which is a trace of rho and the displacement operator in r prime equals 0 and p prime whatever, okay? But now, what is the displacement operator for x equals 0? So we come back here again. The displacement operator for x equals 0 is just the translation operator in momentum space, okay? So this is equal to e to the I over 2 px, okay? Then now I can do the following. I can be smart and I can do, okay, we need to perform a trace. And here we have an operator that depends on position, right? So then I can perform the trace in the eigenbasis of the position operator. If I do that, so let me write it down, dp prime for pi r, I keep the exponential, and now I write the trace. The trace in this continuous basis means that I have to do something like this, okay? And of the operator that it's inside the trace. And inside the trace, I have the density operator, and I have the exponential of I over 2 p momentum position operator x. And sorry, I keep forgetting some primes. So this is p prime operator x, and in here, of course, we had a prime. Okay, so then now this operator, so this is an eigenstate of this operator, so we can bring this out, okay? And then we can rewrite this expression in this very simple form. So let me, oops. So I made only one, so I want to make one change because we have already here x. I cannot call x to the integration variable, of course. So let me call it x prime again, okay? So I hope it's clear. And then now I put this integration over x prime. And I combine this exponential with this exponential, okay? But now acting on x prime, it gives me x prime in the exponent. So this exponential overall is just the integration over momentum. And then here I have I over 2 x prime minus x p prime. And then here I get x prime rho x prime, okay? So if this is clear, then now this thing here, once again, is another delta function, this time of x minus x prime, which means that we get to prove exactly what we wanted, that we can remove the integration over x prime, exchanging x prime by x. So in other words, the marginal of the Wigner function, so integrating out the momentum, we get the probability density function for position measurements, okay? So any question here? You see that there are a few like technical steps, but everything is just substituting and being smart about choosing in which basis the calculation is simpler. But yeah, this kind of calculations is what appears all the time in the properties that I am going to show you, in the proof of the properties that I am going to show you. So you can proceed in the same way for the momentum distribution. So you can integrate out the position and you will get the PDF for momentum measurements. And I encourage you to do it on your own and see if you really understand how to do this derivation. But now, what we will do is I am going to give you a few more properties that I will not prove because it's a bit boring, especially online, I guess. So I will just show you the properties and we can discuss them. So, okay, the first property after this one that I want to give you, so the second property overall, is that this Wigner function is real. So this is a real function, real defined function for every, it doesn't matter which point in phase space you choose and which state you choose. For every state and every point in phase space, it's a real function. On the other hand, it's also trivial to show, especially from the previous proof, that if I perform the integration of the whole of the function over the whole phase space, I just get 1. So in other words, this is a normalized function, okay? This is absolutely clear because if the integration over momentum it's equal to the probability distribution in position, if now I integrate for all positions, what I get is just the sum of all the possible probabilities in X. And that has to be equal to 1 by definition in quantum mechanics. And the proof is just like that, actually. So then I give you some more interesting properties. So the fourth property would be something like this. So what happens if I want to evaluate the expectation value, so the quantum mechanical expectation value of some function of x and p that I can always rewrite as a product of xm times pn, or a sum of those using a Taylor expansion or whatever. So the expectation value of x times p with some powers. So what you can prove, and you can see in the notes, is that this is actually equal to the average with the function, so with the what we could call a distribution in phase space of the corresponding phase space variable. So in this case, x to the m and p to the n. So this allows you to calculate quantum expectation values as just averages of phase space functions, let's say classical functions, with the probability distribution Wigner function that we have defined. Just one special note, of course, in here the order matters because position and momentum do not commute. So it's not the same x to the m, p to the n, that p to the n, x to the m, or anything in between. And what you can prove is that the actual thing that this is equal to is not this one, but the symmetric version of the function. So remember, we discussed already what is the symmetric version of this function when we were talking about basic quantum mechanics. And actually, one of the postulates that we introduced is that quantum mechanical observables can be found from classical observables just by symmetrizing the classical observable with respect to the orderings in position and momentum, and exchanging the variables position and momentum by operators position and momentum will satisfy canonical commutation relations. So in other words, this is actually the nice expression because it's telling you how to calculate expectation values of observables, because observables are always symmetric in position and momentum in order to be Hermitian, with just integrations over phase space, okay? So very quickly, just so you remember, so if I ask you the symmetric of this, I hope you remember that this means that you have to take the two operators x and one operator p and put all the possible orderings. So it would be this. Okay, You just add all of them up, and then you kind of normalize them to the number of elements, okay? So this is what we already defined, but just to make sure that you have it in mind. Okay, so maybe I don't remove it, I just make it small, and I put it next to this expression. Okay, so then one more property that is also very interesting is that if you integrate the function, okay, in all phase space, but you don't integrate just the function, so this would give you 1 because it's normalized, but the square of the function, this tells you that it's bounded by 1/4 pi, okay? And this is a very important property because it tells you that there are no divergences. So if I tell you that the distribution is normalized, okay, this still doesn't tell you that there are no divergences. So for example, the function could diverge at what point, okay, going to infinity, if at some other point it goes to -infinity. And then when you do the integration over the whole space, this plus and minus infinity cancel each other. But if you take the square of the function and you prove that it is bounded, then this automatically means that there are no divergences, because if there would be divergences, they would not cancel out with the square and it would not be bounded, okay? Then just two more properties. The first one is that something that we could call unique state correspondence, which means that you can uniquely define the quantum mechanical state from the distribution. And in particular, you have this formula here that it's sometimes useful. That simply tells you that if you take the characteristic function chi, so the Fourier transform of the Wigner function, and you multiply it by the displacement operator dagger and integrate over the full phase space, then you get the state of the system. So this means that not only the Wigner function is defined by the state, okay, but there is also the opposite relation. If I give you the Wigner function, you can find the state, and this is a unique correspondence, okay? And this is important because this tells you that all the information contained in the state, it's also contained in the Wigner function. So you can choose whether you do quantum mechanics with the state or quantum mechanics with the Wigner function, okay? So just one more property. This property, I give it to you because it's useful for calculations and because it's also historically important, which is Wigner's original formulation. So Wigner didn't give us the Wigner function in this, let's say, nice way with traces and the characteristic function and the displacement operator and so on. He did it in a different way. What he found, or the distribution that he defined naturally in the problems he was working on, was the following. You just take the probability of making a jump from one position x plus y over 2 to another position x minus y over 2, or the opposite, from x minus y over 2 to x plus y over 2. So this is the probability, or the probability amplitude of making a jump of length y, okay? And you just do the Fourier transform of that. So you do the Fourier transform. And that's the Wigner function. So the Wigner function can also be seen just as the Fourier transform of the probability amplitude of making a transition of length y in real space, okay? Okay, so these are essentially all the properties that I want to define first that make sense in the sense that they kind of show you that this function that we have defined could be indeed a distribution. So we have been able to define in phase space a distribution Wigner function that is giving you all the properties that you expect from a distribution. It's bounded, it's normalized, it's real. It allows you to calculate expectation values or averages of any observable. It contains all the information of the state of the system. So in principle, everything is very nice. However, and here comes the final property that makes everything very interesting and makes quantum mechanics go beyond classical physics. So is the following. So before giving you the final property, let me just tell you that you can also prove that the overlap between two quantum mechanical states, ρ1 and ρ2. So as I'm going to show this function here, the trace of ρ1, ρ2, for pure states, this would literally be the overlap between the two pure states. So this thing can be calculated just as the overlap between the corresponding Wigner functions. So you take the Wigner function associated to state 1, the Wigner function associated to state 2, you do the overlap, so the integration of their multiplication, and you get the corresponding trace in the Hilbert space. So, but now what happens if I consider that my states are pure states? So as we have seen before, the trace of an outer product, it's equal to just this expression in terms of inner products. So in particular, this is equal to psi1, psi2 squared. So it's the overlap between the two pure states. And of course, in quantum mechanics, I have no problem choosing two states that are orthogonal. So I can choose two states to be orthogonal. I mean, I can just choose two states that are orthogonal for this expression, and I will get 0. But this is amazing because I am telling you that the overlap between two functions in phase space is 0. And the only way this can happen is if at least one of them is negative. I mean, it has negative values. So let me write it down. So this automatically implies that omega, W, so the Wigner function of some state ρ at some position r is negative, okay, or can be negative for some values of the quantum mechanical state that you choose and the position in phase space that you choose. Okay, so this kind of destroys a little bit our hopes or our expectations, because then this means that the Wigner function, it is not a true probability density function in the classical sense, okay? Because it can take negative values. And another way of saying this, and of course we could have known this from the very beginning, is that quantum mechanics is not equal, okay, to just adding noise, so just classical noise that makes things wobble and then it creates a probability distribution instead of a well-defined point on classical mechanics. Okay, I mean, thank God that this is this way, because we have created a full new theory called quantum mechanics that is very weird, and it's full of completely new mathematics and so on, to describe all this randomness, all this probability in probabilistic nature that we observe in nature. And if now I would show you that this is equivalent to just having classical noise to the system, then what I would be telling you is that I can simulate. So I can pretend to have all the quantum mechanical effects just by adding noise onto my classical systems. So this is showing that quantum mechanics really goes beyond what you can do in classical mechanics, even if you include uncertainty, even if you include, noise in the system. So then quantum mechanical uncertainties really go beyond what you can do with classical mechanics and distributions, okay? So then, therefore, we cannot call the Wigner function a distribution or a probability density function. We usually call it quasi-probability distribution because it satisfies almost all the properties of a probability distribution, except that it can be negative. But still, because it's a bounded function and it's a real function, we can always plot it in phase space, okay, including the negative values. And this gives a visual way of recognizing quantum mechanical states in phase space. So let me give you an example or a family of examples. So I am going to give you the family of examples that is the following. So I am going to give you the Wigner function of Fock states, of the number states. So this is, so the proof of this expression, you have it in the lecture notes. Please go through it again and let me know if you have any problems with it. So let me write it down and then we discuss it. Okay. Oops, this depends on R squared. Okay, so this L is just the Laguerre polynomial of order n, okay? Then we have an exponential that bounds the state, so the states are normalizable. And then we have this minus to the n that gives all the spies, as you are going to see. So this is the Wigner function of Fock states. It's not very difficult to find them, so you can check. And then I give you a plot of this function. So I hope you can see it well. So let me explain you. So let's consider the first one. So the vacuum state. So as you see, the Wigner function of the vacuum state is very simple. It's just a distribution that is centered. So this is the p-axis. This is the x-axis, okay? So it's just a distribution that is centered at the origin of phase space, and it has some kind of noise around it, okay? So this one is what we could call a classical distribution, classical noise, and so on. However, when you go to the Fock state one, what you see is that in the center, the probability distribution or this function becomes negative. And in particular, in this plot, whenever you see red, it means positive. Whenever you see blue, it means negative, okay? And the higher the contrast, the higher the function. So then the maximum of this distribution is actually at the origin of phase space as well, but with a negative sign. And this is very simple to see because when you come to the functional form of the Wigner function, you see that you have a -1 to the n, okay? On the other hand, the Laguerre polynomials at r equals 0, so at the origin of phase space, are equal to 1. So ln of 0, it's always equal to 1. So therefore, what you see is that all the odd Fock states, all Fock states with odd n, will be negative in the origin of phase space. And this is exactly what you see in here. So you see that Fock state 1 is negative in the origin, Fock state 3 is negative in the origin, and it has like oscillations, okay? And Fock state 2, it's positive in the origin, but it has oscillations along the radial direction that become negative outside of the center. So you see that except for the Wigner function of the vacuum state, the Wigner function of the other states cannot be considered probability distributions. But now I want to give you kind of a positive feeling about these negativities, because the fact that Wigner functions can be negative allows you actually in experiments to have a smoking gun for quantum phenomena. So let me just write it down. So I want to remark that negativity, so if you want negativity is, sorry, is a smoking gun for quantum phenomena in experiments. So what I mean is the following. You design an experiment, you want to find quantum mechanical phenomena, you want to test that your system is really a quantum mechanical system. It's not easy to see quantum mechanical effects, so then you work very hard, okay? We will see how difficult it is to see quantum mechanical effects. You work very hard, you create your system, your experiment, and then if you find evidence that you have a negative value of your Wigner function, the Wigner function can be evaluated experimentally because it's related to positional momentum probability distributions. So just measuring positional momentum, you can reconstruct the Wigner function. Then if you find that it is negative somewhere, then you know that your experiment is really in the quantum regime. Okay, so it's really not described by classical physics. So this is why it's very interesting to have the Wigner function, or one of the reasons why it is very interesting. And I hope that I have convinced you of this. So any questions up to here? So I know I didn't make too many proofs, but please go through the proofs in the lecture notes, and any conceptual question that you might have now or later, just ask me. So if this is clear, then what I will do now is that even though I'm telling you that quantum mechanics requires negative Wigner functions, so negative distributions or distributions that can take negative values, there is still a class of states that are described by positive distributions, but are very important because are the most natural states in experiments. And I will explain all this in detail, and these are called Gaussian states. So now I will discuss what I mean by these Gaussian states. So essentially Gaussian states. So Gaussian states, let me give you a definition. So Gaussian states are states for which the statistics are defined, so are completely defined, as you can imagine from the name, from first and second order moments. Second order moments. Okay, and in particular, I mean things like the expectation value of the quadratures and the expectation value of a multiplication of two quadratures and so on. So just like in classical physics, Gaussian distributions are kind of the most important distributions that we study, and they appear everywhere, and we can kind of associate Gaussian distributions with many real processes in physical systems as an approximation in the worst case and so on. we can do the same with quantum mechanical states. We can find what are the quantum mechanical states that are completely described by first and second order moments. And of course, this implies automatically that the Wigner function is a Gaussian probability density function. So in particular, it's a Gaussian means that I can always write it as a quadratic form of the phase space variables. And the most general quadratic form I can write will always have this form in here. Where I have defined two objects. First, I have defined a vector D and a matrix B, and I will explain in a second what they are. If you have studied probability theory just in mathematics, you already know that this is just the mean vector and the covariance matrix of a normal, of a standard Gaussian distribution. And then we need some normalization factor in here. That is the determinant of B, essentially. So the square root of the determinant of B. When working with Gaussian distributions, it's always important to keep in mind Gaussian integrals, okay? And in particular, this Gaussian integral formula that I am going to give you now, it's very interesting to remember. And it's just the following. So if I perform the integration in an n-dimensional space of any quadratic form, so I just have a quadratic form defined by a matrix A and a vector X, okay? This you can show, and probably you have seen it already in your math courses. This is one of the typical proofs that you do in calculus in your first year. You can see that this integral, the integral of a Gaussian function, is another Gaussian function of the vector X. So let me make sure I put all the factors correctly. Okay, so we have this integral Gaussian formula that it's always very interesting, and we will not use it a lot now, but we might use it during the course, and also it's so important for many things that I just want to remark that this is something that you should be familiar with. And in this case, this is the formula that allows you to see that this Wigner function is normalized. So if you calculate the integral of this function here using this integral Gaussian integral theorem, then you will find that precisely the factor that appears in here is exactly 1 over, so it's what you need to normalize it. So, okay, just with this remark, let me just make this small and bring it here. So with this remark, let me now give you a bit more feeling about what is this distribution. So in particular, this Gaussian distribution, again, is defined by first and second order moments, which means the mean vector and the covariance matrix. And in particular, so as I said, the mean vector probably from your math courses, you know that the components of the mean vector can be evaluated just as the name suggests by doing the average of the corresponding phase space variable, okay? This is, you also have the proof of this in the lecture notes, but it's kind of natural, and if you have studied probability theory, this is something that you probably know already. And the other interesting thing is that the covariance matrix, which has elements V, J, L, this can be related to a second order moment expression that looks like this. So it's literally the second order moments, not of the variables themselves, but of the fluctuation of the variables. Okay, so here, when I say fluctuation of the variable, it simply means, or let me put it in vector form so you get used to vector expressions. I mean that I take the phase space variable and I subtract the average of the distribution. So this is like the variables referred to the center of the distribution, okay? So these two expressions are something that you might know from just classical probability theory, but now using this property of the Wigner function, so using this property here of the Wigner function, okay, that relates phase space moments with quantum mechanical moments, then we automatically see that this is also equal to the expectation value of the corresponding quadrature, okay, and that this is equal to the expectation value of the symmetrically ordered quadratures, so product of two quadratures, which I can always write in this way. Okay? Oh, sorry. These are fluctuations of the quadratures. And from now on, every time I say fluctuation of an operator, okay, I always mean I take the operator and I remove the expectation value of the operator. So it's the equivalent expression that we had for the phase space variable. And these fluctuation operators are very interesting because they allow us to write the variance, for example. So they encode the variance in the following way. If we calculate the expectation value of the fluctuation operator squared, that's the variance directly, as you can check. And then just a couple more simple things. Of course, in vector form, I can always define, or I can always say that my mean vector in the Gaussian distribution is equal to the expectation value of the vector of quadratures, okay? So this is an expression that you have to keep in mind. And then in matrix form, I can rewrite the covariance matrix in terms of quantum mechanical expectation values in the following way, using the commutation relations. So remember that RL with RJ, you have a commutator between them that it's equal, as I defined at the beginning of this section, it's equal to this symplectic form. So then it's no surprise, I hope, that you see that we can write the covariance matrix just as the expectation value of all the possible products of the position, sorry, of the quadrature vectors. So again, this is a column vector. This is a transpose, so this is a row vector. So then this overall is a 2 times 2 object, okay, when you do the matrix multiplication. And then to this, you can just subtract I times the symplectic form. So this is an expression that it's also very useful because it allows us to write the covariance matrix in a compact form in terms of the quadrature vectors, okay? So this is the definition of Gaussian states. So a Gaussian state is a state that is completely defined by first and second order moments, which implies that the Wigner function is a Gaussian function. Now, the Gaussian function is defined by two statistical objects, the mean vector and the covariance matrix, that have a direct relation with quantum mechanical expectation values, okay? So any higher order moment okay, can be found from what you might know also from probability theory, that it's called the Gaussian moment theorem. And the Gaussian moment theorem simply says the following simple expression. It simply says that if you want to evaluate the moment of order n, so this means that you take phase space variable J1, phase space variable J2, all the way to phase space variable Gn, and you multiply them. So Rj could be X or P. Then this is equal to either 0 for odd n. So if n, so if the number, so if the moment that you are seeing, that you want to evaluate is an odd order moment, so which means that you have an odd number of variables here, then this object is 0 automatically. And otherwise, this is equal to the following. You just take products. So you do the sum of all the products of second order moments, in particular of covariance, of the elements of the covariance matrix that we have defined. So let me write it down first. So we do the multiplication of all the possible covariance. So this is for even n. And then now the point is that these indices I1 to In, they take values over all the n-1 double factorial ways in which we compare J1, J2 up to Jn. So this is known as the Gaussian moment theorem. Okay, and just so you understand this, because I know this is a bit abstract, so it's a bit difficult to grasp exactly what it means. So let me give you specific examples. So I give you first example 1, which is just, let's particularize this expression to n equal 4. So n equal 4, what does it mean? It means that we just take the moment of, so the moments of order 4, let's say we put here delta R1, delta R2. So let me do it a bit different. So let me just do it this way. Okay. So I tell you, imagine that I want to evaluate this moment here. So I want to evaluate the moment associated to XP, XP, okay? Fourth order moment. So according to this expression, this would mean the following. So when I write here, this is equivalent to saying delta R1, delta R2, delta R1, delta R2. Agree? So essentially we have the phase space vector, which has two components, X and P, and then R1 is X, R2 is P. So what I am saying here is that now we have to take this expression here, which tells you will have the multiplication of two covariance matrices, and the indices of these covariance matrices will be all the possibilities of combination of these indices here, okay? Of pairs of these indices. So in particular, I write two covariance matrices and I say, okay, the first order would be 1, 2, 1, 2. So I just write it 1, 2, 1, 2. Now I can do a second ordering that would be 1 with the third index 1 and 2 with the fourth index 2. So this would be V11, V22. And finally, I have the first index with the fourth index, which is 1, 2, and the second index with the with the third index, which would be V1, 2, V2, 1, okay? So essentially, this is what the Gaussian moment theorem tells you for n equal 4. And you can proceed in the same way for any other moment of order 4 or any other moment of any order. Of course, the covariance matrix is symmetric. So V12 is equal to V21, okay? So that's also interesting to remember because then this term is equal to this term essentially, and things like this. So just to give you a feeling of how to apply this expression. And now to give you a feeling of how to evaluate quantum mechanical higher order moments from this expression, let me tell you how to evaluate, for example, x to the cube. So if I ask you, what is the expectation value of the quadrature x to the cube, so to the third power, when you are in a Gaussian state? So then this is very simple because the only thing that you need to do is use the Gaussian moment theorem in the definition of the mean vector and the covariance matrix. So in particular, the first thing, because in the Gaussian moment theorem, what you have are fluctuations. So it's the fluctuation operators, it's not the operators themselves, or fluctuation variables, not the variables themselves. You first write the operator in terms of the fluctuation operator, okay? Now you just expand. So you have a sum to the cube, so you just use the binomial, the Newton binomial formula to expand this, and you get the following. So the cube of the first one, then 2 times the second one, times the square of the first one, 2 times the square of the second one, and the first power of the first one, and then finally the cube of the second one. So this is just the expression that you get, and now you see automatically that this thing here is 0 according to the Gaussian moment theorem because it's a moment of odd order. Then you see that the same happens here. This is 0 because it's a first order moment. So it's an odd order. Then on the other hand, this thing here is the variance of x, or in other words, this is just the covariance matrix element 1, 1, okay? And then this thing here is the element 1 of the mean vector. And well, the same we have around, okay? So this thing here is just the element 1 of the mean vector to the cube. So then at the end of the day, you can write this expression, so this moment as d1 to the cube plus 2 times d1, d11, okay? So this allows you to write a quantum expectation value of high order, like third order, as a function of just elements of first order and second order, okay?
Sorry, a simple question regarding to the
yes.
last of this page. I really think the expected value of x cube is d1 cube plus 3 times d1 v11. Yeah.
So you are completely right that it's 1, 3, 3, 1, of course.
Yeah.
So any more questions? So otherwise, if there are no final questions, then I let you go and have a nice week and see you next week at 12:55 again on Wednesday.